So today, color correction. So we have already seen this presentation of the primary colors, the red, green, and blue, and we already know that if you mix a couple of colors, then what you have is another color. So you have red and green with yellow, and now we already know that because these things are vectors, depending on what is the weight of the red and green channels, you will have different tones of yellow if you want. So it will be more yellow or less yellow. It will be yellow, kind of yellow color. And we have three numbers. So we have red, green, and blue. So we can think of this as a vector in some color space. So we will have the red, green, and blue axis. And then if you are given a color like this one, that is 184, 95, 12, so you will travel 184 units in the red direction. Then you will travel 95 in the green direction, and then you will travel 12 in the blue direction. So given a color for a point, it's nothing more than is defined in a vector. And you can define your vectors. This is the standard vector notation that you have used in linear algebra. So it is how much you have to travel and a unit vector in the direction of that travel, that tree. So you have to take 184 units in the red direction and in the green in the blue. Okay, so a color is nothing more than a vector. Okay, and then we can define our color field. So you have the three dimensions. So you have red, green, and blue. And then for every combination for every vector that you have in this space, you will have a color. So here we are representing those colors. And if you add red and green to the maximum intensity, what you have is yellow. And along all this line, you have different tones of yellow. And depending, for instance, this color too, it is not in the diagonal, but it has a little bit less, it has a little bit more green than red. So it's a different tone of yellow. And the farther you go, so if you add less and less and less red and more green, then you are almost green. Okay? So yellow as such is not very well defined color. All this red is kind of yellow. And we may define the red, green, and blue. But if it is a color space, you can define any other axis. So you can define this as your basis vector. So you can define now cyan, yellow, and magenta as your vectors to describe a point. So you can express a point here telling you how much you have to travel in red, green, and blue, or you have to describe, or you may describe the same point, but now how much you have to travel in the cyan, yellow, and magenta. And why these three colors? Because they are in the diagonal. They have an interesting property. So let's say that in the monitor, with light, you don't put any intensity in red, green, and blue. So you don't put any photon. What is the color that you have? You don't put red, green, and blue photons. What do you have? Black. So if you don't do anything, you get black. Okay, now let's think of printing. If you don't put any ink, what is the color that you have? White. Have white because the paper is white. So it is the opposite. So red, green, and blue are said to be so I have a color. So let's say I have my color C. My color C is whatever you add in red, that's whatever you add in, that's whatever you add in blue. And this is an additive color space. If I add a lot of color, then what I have is white. But I can describe the same color now in my, let me put it in the same order, cyan, magenta, and yellow. No, no te perdonamos. Cuéntanos un chiste. Natalia, tú también. Marta también.
¿Por qué hoy es mojada va al gimnasio? Porque está cuadrada. Porque no se debe nunca ir a la cocina, tenemos que ir por eso.
Well, that's all the man, not me. Okay, so we said cyan, magenta, and yellow. So these are now our vectors, and you can add also, you can reach the same color, but now with this, I mean, I do a lot of effort. I put a lot of ink. What do you get? You put a lot of ink of cyan, a lot of ink of magenta, a lot of ink of yellow. What do you get? Black. Okay, so this color space is called additive. This color space is called subtractive. And you can reach the same color. So only that you need to find what is the right amount of ink or the right amount of light. But you can reach all the same color. Okay. So this CMY axis, have you found them before? No? You have never seen the CMY? Three letters together ever. Okay, there is another one that is interesting. So we have, yeah, we will come back to this idea a bit later in the course, but instead of CMY, so we have said that the color space is a three-dimensional cube. So if it is three-dimensional, you only need three basis vectors. But typically, we also add a fourth one that is black. Okay, and the reason is that, what do you think if I want to print something black and all text pages, they are all black, mostly of them, so it is black ink. So what do you think it is cheaper to reach a black by adding three different kinds of inks, or use this one, just one? This one is cheaper. So now we may use four different vectors. So you can also here this one to reach a color. What is the difference? Why, if it is a three-dimensional vector and you use three basis vectors, what do you have? A basis. Okay, so you have a basis. A basis in the algebraic sense. If you use four vectors, so now C and Y, also RTB, they're basis. So basis means this set has three vectors that are linearly independent, and you are representing vectors that are three-dimensional. So with three linearly independent vectors, I can always reach any vector in this space. If I have now another vector, now I have four vectors. Is it the basis? This is not the basis. So if these vectors are three-dimensional, you have four vectors. One of them necessarily have to be a linear combination of the other three. Okay. And which one? All of them are linear. So your K is a linear combination of these three, but also C is a linear combination of these three. So all of them are linear combinations of the others. So this is not the basis, but it is a generating set. Generating set. So meaning you can reach any point. You can reach any point by a linear combination of the four. But 4 is not the minimum that you need. So that is why it is not a basis. It's a generating set because you can reach any point with these 4 vectors. It is not a basis because you need 3, you don't need 4. Okay, good. So, yeah.
Why is it only the CNY?
Yeah, you could also do it in the RGB. Okay, so then what kind of things can we do? So we can take, for instance, an image, and you can take the red channel and apply a gamma transformation. We already know the gamma transformation. So you can do it with gamma equal 2, and then the red and green channels, sorry, the green and blue channels stay the same, but the red one is the form. And we already know why we have these holes here and why we have this peak. So they are related to rounding. Okay? And they are related to rounding, and also we will get peaks where the histogram is compressed, and we will get holes where the histogram is expanded. Okay, good. So we can make the image more red than it possibly can be. Make it less red. So if you make gamma equal 0.5, make it less red. So if you make it less red, and you think of the color disk, what you are doing is shifting in the opposite direction of red. So we are making it more cyan. And yeah, we can play with this with all the other channels. So all these are with the different channels. Green or less green, or blue, or less blue. So you make it weird. And here comes a little bit of question. That is, okay, we may describe the color in the RGB, but we can also describe it in a system that separates color from intensity. There are many of these. So this is one of them. We will see another one. So you have luminance, and then 2 channels that are called A star chroma, B star chroma. So whatever the composition you do, you will have one that measures how many photons you have, depending on their wavelength, and another 2 channels that describe what is the wavelength that you are getting. Okay, so yeah, we will see this one. That is even this one, luminance, hue, and saturation. We will not see the details of this one. We will see the details of another one that is called HSV, and they all share the same kind of ideas. So just seeing one of them is enough. So, but the idea is that, yeah, our eyes see in RGB because we have red, green, and blue sensors. But the brain somehow combines all this information, how many photons, how much light you are receiving from that point, and what is the wavelength, and what is the color of those wavelengths. So given the color Q, we can draw some interesting regions. So one of the interesting regions is this. So we define the value. Do you remember the value? Value of the average of the three channels. So the value of an image, we said that this is taken. like this. So the value of an image was 1/3 of the R plus T. So how much you had to travel in the three directions. So this was the value. Instead of the value, we will define. We will define a plane that is all those colors such that this addition is constant. It's a given value. You choose C. You choose C, and then you look for all the values that R plus C plus B is equal C. You call it pi C. So this is the set of all colors such that this holds. So this color here belongs to the plane BB. Take the 3 to the other side. So this particular color belongs to this plane. How do you know that this is a plane? This is the what is the equation of a plane? X has to be y 6 divided like this plus b. Consider this is the equation of a plane, isn't it? And why is it a plane? Because we have three different values that we can change. We have these three values that we can change. And we have only one constraint, that is this equation. So you have 2 degrees of freedom. In a plane, you have 2 vectors. You can travel freely vectors. So in this plane, you can travel freely in this direction and in this direction. But there are 2 dimensions which you can move. They're constrained because you cannot travel away from the plane. Actually, if you want, we can define. So you can define this vector. This is perpendicular to the plane. This is the vector, let's say B, and B in our case is ABC. And then this plane is defined by all points such that this inner product is given. So let's expand that. So we have B, that is ABC. Not sorry, it's not 0. It's erase. It's not here. It's not there. Erase. Yeah. So this is not. But it is constant. Okay, so it's minus B, that equation. So times x, y, z, so 1 minus 3. So this is our plane. Okay, so now we are interested in this one. So this one is 1, 1, 1 times RGB of C. This is our plane. What is 1, 1, 1? It's a vector. It's a diagonal vector. Goes away from the origin. So it is vector here. So the origin is here. So here is the origin. So this is the 1, 1, 1 direct vector. So it is the vector that goes through the diagonal and it goes to the other corner of the cube. That is the 1, 1, 1 vector. So we are interested in this plane. So we are interested in the plane of all the colors such that the addition of the 3 is C, and the value is C divided by 3. This is the same as I was saying here. Again, at this point, belong to the 3B plane. Okay, now, okay, so now we can think of what is the intersection between this plane and the color cube. So, and here we have drawn one of those intersections. So we have a plane, you have the color cube, and now you can represent all the colors that belong to the same plane. All these colors, they have the property that R plus E plus B is equal to C, and C in this particular case is 255. And for instance, interesting points. So this point is a pure red. The pure red belongs to that point because it is 255.00. But the pure green also belongs to that plane because it is 255.0, and the pure blue is 0.0. So they all belong to the same plane. And we can now think of the intersection between this plane, that is R plus E plus B equals C, and this plane. It's this plane. So let's take it here to be here. So let's say that I have my three axes, R, G, B, and I want to focus in this plane here. So that one on the back. Okay, so what is the equation of that plane? R equals 0. That is the equation of that plane that I can also write as 1, 0, 0 times RdB equals 0. So all planes can be put in this form. Okay, so it is the vector perpendicular to the plane times your follow vector equal a constant. So this is our equation. Now, again, now we have two equations. Well, we have R equals 0, this one, but we also have R plus T plus B equal C. So now we have two equations. How many degrees of freedom do you have? So let's make the degrees of freedom red. So we have 3 degrees of freedom. So I can travel in 3 different directions. But if I can travel in 3 different directions, but I have 2 constraints, I can travel in a line, a plane, the whole cube. How many degrees of freedom do you have? You have only 1 degree of freedom. So you have to travel in a line. It is very easy to see what line it is. So R is equal to 0, so R disappears from there. And then you can travel in the line B equals C minus G. But you have only 1 degree of freedom. That is this one. So you change G, C is a constant. You change G, and then automatically you are given B. And all your points are defined. All your points are defined by red. Red has to be 0. G is free, and then blue, but blue is C minus G. So you have only 1 degree of freedom, that is G. So you can travel over 1 line. So this is these lines. These are these lines that are represented here. So these lines here, they are the lines such that R plus B equal to 55. So I made my example with R equals 0. They made this example with with G equals 0. Okay, but along this line has this kind of shape. So they have this kind of expression. So given one of the channels, you compute the other, and then you can go from completely red to completely blue, and then all colors in between. And what if my C is larger than 255? So if C is larger than 255, but it's smaller than 510, then the intersection between this plane, and the color cube is no longer a triangle, but it is an hexagon. So now we have an hexagon that is our intersection. And again, you can compute what is the intersection between this plane and this plane on the wall, and will be a line. Again, the intersection between two planes is always a line. Okay, so for instance, for C equal 383, this is the intersection, and then it goes, I don't know, from violet to some kind of red. What else? Yeah, you can compute many different intersections. Okay, so this plane is intersecting here, it is intersecting here, it is intersecting there. So you can compute all kinds of intersections. And then, if you look from the front, and you keep increasing the C, so you make C smaller, this is what you see. You make C larger, this is what you see. Then, let's go now for HSV. So HSV is one of these representations for which we decompose into an intensity channel and two channels that describe the color. Okay, so let's start with a point. So we will start with the color that is R0, E0, V0, and then we compute what is the plane to which this point belongs. So it belongs to the plane such that R plus E plus V is equal to the sum of these three values. And then in this plane, there will be a point such that R plus V plus 3 plus B, RD and B are the same. Okay, so let's do this step by step. Okay, so we start with a point. So we start with this point. We know that this belongs, let's use the right notations. So this belongs to the plane such that the plane R0 plus G0 plus B. That is, all the points RGB such that R plus T plus B is equal to R0 plus D0 plus B0. Okay, now in this plane, what I claim is that there will be a point that has the shape, that has the value x, x, x. So there is a point here that has the three components to the same value. And it also belongs to this plane. Which is that? Which is that point? Which is that point? It is very easy. R plus T plus B divided by 3. This is the value. So the value, so the point that has value, or we know if you want. So the point that has these three values, all the same, it also belongs to this plane. What is it? This is V0 times 1, 1, 1. So it means it has to be on the diagonal. So in this diagonal, so let's say that we have this intersection between here probably. So we say here is the origin, here is the diagonal. So there is a point there in the middle where this diagonal that crosses the plane. At that point is the V0, V0, V0. Clear? And there is a property of these points. So all colors for which the three values are the same, all these colors, all of them, they are gray values. Actually, there are a couple of them that we already know. 0, 0 is black. And the 55, the 55, the 55 is white. These two we already know. And then we have all the gray values. All points for which the three numbers are the same, they are gray for sure. Okay, and these points are located here in the middle of these planes. Okay, so given an RGB color, I can always compute this point in the middle of the plane. So this point in the middle of the plane will be the value, and then times the 1, 1, 1 vector. And but this is not my color. My color was here, so it belongs also to the same plane, but it is not there. It's a little bit away from that point. So I can define the vector that goes from the gray point in the plane, that is only one, to my color. This will be this S0 vector. So S0 is my color minus the V0, minus the gray. So it is that vector. And then I can measure a couple of things. I can measure what is the length of this vector. So this is my length. And I can also measure what is the angle between these gray values. You join it to the maximum red value that is in the plane. So one of the values in the plane will be completely red. So you draw this line, and then you measure the angle between this line and this vector. That is a well-defined measurement. So your question, what is Q? Q formally is this angle. What it means, okay, it is very so the intuitive description. It is something related to color, right? It is not something that we can easily describe. So formally, it is very easy to describe. This is the angle between this vector and who is this vector? Okay, so we said the maximally red point. So the maximally red point is this one. It is the point that belongs to the plane and that only has a red component. And then this line is that point minus the gray point. And we measure the angle between this vector and this other vector, the S0 vector. And now we have our conversion. So you have an RGB point, you want to convert to HSV. So H is this angle, S is the length of the S0 vector, and V is the length of the V vector, the V0 vector. And we have simply changed our information. We have 3 numbers at the beginning. Now we also have 3 numbers. And given RGB, you can compute the HSV and vice versa. So you have not lost any information. So if you can invert, you remember this was one of the first ideas in the course. if a transformation is invertible, you don't lose information, and you can recover RGB from the HSP. So that is something that we will see now. Yeah, so just a little bit of illustration of this kind of things. So let's say that we have the color Q, the origin is here, the origin is there. So we have a point in that color Q, and so that is the color that we want to represent. Now, this is the color that we want to represent. Now we draw the 1, 1, 1 diagonal. All of them are gray values. So this is the 0, 0, 0. This is the 255 Q. So we have go from black to white, and all the points in between are gray. And this was the color that we wanted to use. So now you compute the vector that goes from the gray point in the plane to the color vector. This is V, and you draw the line of the vector that goes from the gray point to the maximally red point in the plane. This is this vector, and then this angle is the hue. Okay, so this is again the same slide. Here are so we will take the color Q. So this is somehow representing the walls of the color Q, and we will make R plus D plus B equals C, and we will make C larger. Okay, so now C is a little bit larger. Have the value. Okay, so at value 0, value 10. Up to a point is a triangle. And if you keep increasing the value, now you get hexagons. Now you have an hexagon. Once again, the triangle. Until you go out from the cube. Okay, so now we said we can go from RGB to HSP. So we can very easily do that. So V is you could take the RGB, you compute C. The value vector is 1/3 of this one. The value is simply 1 of the components. And the length of this vector is this one. Okay, so the length of this vector is the value of this thing that is related to the value. Okay, and then we have defined S naught. S naught is this. And this is the length of S naught. And then we have to compute the angle. Okay, so we have to put the formula for the angle. So what is the maximally red vector? Maximally red vector is C00. And we subtract the gray point. It's this one, this vector. Now we have to measure the angle. So this is the maximally, so this is this vector that goes from the gray to the maximally red. We have defined the difference between our color and the gray, and now we have to measure the angle between them. To measure the angle is simply the arc cosine of this dot product divided by the normal. So now we have everything, because given RGB, in RGB you can compute V0. From V0 you can compute the length. You can also compute this vector. You can also compute its length. Then the angle is also something that we can compute. We can compute X, that depends on our color, because our color is defined in C. And then with x and s naught, we can compute the angle. And but it is typical to normalize the saturation. So this length is called the saturation. So this is not. So the saturation, you can compute what is the. So if it is very little saturated, this vector is very small. Okay, so the larger the saturation, the larger this vector. Okay, so let's say that this vector, our color is not saturated. So we have saturation equal 0. Then what can you say about the color? You have a color whose saturation is 0. What kind of color is it? Is it gray? Okay, so all gray colors, they don't have any saturation. And the larger it goes from the gray, the larger the saturation is. Okay, you can compute in the whole color cube, what is the maximum saturation that you can find. And you can make that calculation, and the maximum saturation is this one, it's the 8. So instead of reporting the saturation, so instead of reporting this number, just report that number divided by the maximum. So now your saturation is between 0 and 1. It doesn't matter, it is just a scalar transformation. And it is always the same. So reporting the length of the vector or the length divided by number is the same. Okay, and then, yeah, this is a little bit. Okay, so now, let's say that you are given the HSP. So the transformation is supposed to be invertible. So how do you discover the RGB? So you are given HSP. So now you are given a point in a plane. You are given what is H, what is S, what is P for that vector, for that color. And then you will define a different coordinate system. So you will define a coordinate system X, Y, V. So V goes in the direction of the diagonal. X goes from the gray point to the maximally red. Okay, so it is the same X that we had before. So we had before from the gray to the maximally red. So it is the same X. And Y is very easy to calculate. If it is a coordinate system, it has to be the cross product between V and X. Okay, so now Y is a vector that is perpendicular to V and X, and this one. Okay, which of the three vectors are in the plane, are contained in the plane, this color plane that we are interested in? None of them, 2 of them, 1 of them, how many? 2, which ones? X and Y. X and Y are contained in the plane, while V is perpendicular to the plane. So in that coordinate system, X and Y, they have the expression 1, 0, 0, 0, 1, 0, and V is perpendicular to it. Both of them, 0, 0, 1. In this coordinate system. So now what we have to do is to find the expression of our color in the coordinate system. So you are given an HSP vector, okay? So that is a point that belongs to the plane. So if it belongs to the plane, it only needs X and Y because it is within the plane. It doesn't need to go out of the plane to represent it. And just a reminder, so this is the color. So this is the length of from gray to that color, and this is this angle. So we can represent very easily that color with X, that is the length of this vector, cosine S sine and 0, because we don't need any V, because the color that we are interested in is in the plane. So S and H are the polar representation of that color in that plane. Okay. So our color in that coordinate system is this one. S cosine H times X, S sine H times Y, and then COV. Okay, so let's make a break here. Okay, so we were here. So we are given an H. So we already know how to go from RGB to HSV, and now we are going the way back. So you are given an HSV point. Now we want to come back to RGB. So for the moment, what we have done is to express that color in the coordinate system X, Y, B. Okay, now. Sure.
This only applies for the plane that is the triangle.
That is a coordinate system that is attached to that plane. Yeah. So if you define a different plane, you have to define a different coordinate system. That's correct. Okay, then. So now, what I have to do is I need to find the, so I already know the, so now we have two coordinate systems. So say that I have my RGB, so this is R and B, these are the unit vectors. I have a plane. I have a plane here. I will draw only the triangle corresponding to that plane. This is one plane. And within this plane, we have defined a different coordinate system. So I have B that goes out. I have X. I have X. X that points in the direction of red. And then I have Y that is perpendicular to this point. I don't know where it goes, but let's say it goes. Okay, so I have X and Y defined within the plane, and then I have B that goes out. So these are my two coordinate systems. And in these coordinate systems, I have a point. So let's say that this is my color. This is the color that I want to represent. So that color will have, let's see what notation we have used in there. Use S. Estamos chequeando.
¿Has hecho ya el descanso? No era por si no estaba en el descanso, pero bueno. Al final de la clase.
¿De qué?
Déjame pensar y concluir al final de la clase.
Okay, so we have the color S. Okay, so we already know the coordinates of S in the X, Y, B coordinate system that we already know what it is. So it is S cosine of H, S sine of H, and then 0 in that coordinate system. But in a different coordinate system, so we want to transfer this to the coordinates of X in the RGB coordinate system. We have different values. And you may remember this from algebra. So whenever you have so let's say that you have now this is general algebra. It is not related to colors. Okay. So you have a vector. We have a vector in the X, Y, Z coordinate system. So we have the X, Y, Z coordinate system. So what is that? This be this one. So some values, and you know that this is equal, or this implies that R is X of X plus Y of Y plus Z of Z. Okay, now I want to find this vector, but now in a different coordinate system that we call U, V, W. So it will have different value. U naught, V naught, W naught, and the point will be U naught down U plus V naught V plus W naught W. And I have to find transformation that tells me how to go from this coordinates to this one. And the trick was to convert these ones into the U, V, and W naught, W coordinate system. So X in this coordinate system. So the basis vector in the U, W was, let's say, this one, X U, X B, X W. And the same for Y and the same for Z. So now, what are you saying here? So I can R. So R in the UEW system will be X naught times that X U, X B, X W plus Y naught, Y U, Y B, Y W plus Z naught, Z U, Z B, Z W. And I can put that in a matrix form and say that this is equal to this matrix. This is a reminder of algebra. I'm sure you know all this. Times. So I did it right. So there is a matrix. So what I have to find is, so as we write this, so a vector R in the UW, UTW coordinate is a matrix that goes from XYZ to UVW, and then the coordinate XYZ. If something is a vector, remind always to keep the value of it, because otherwise it isn't clear whether it is a vector or it is a scalar. And this matrix was the matrix of change of basis. You remember that? So it is, how do you express X in the new basis? How do you express Y in the new basis? How do you express Z in the new basis? So that is what we have to find for the HSV. So that is what we will do now. So we will try to find the change, the matrix that changes the basis. Okay, so let's do it. Yeah, we need to find what is the expression of X, Y, and V in the RGB. Okay, so let's start. Okay, so we know. I think it's really early. Okay, so what is x? X in its own coordinate system is 1, 0, 0. Same for y and same for b. So we need to find what is the matrix such that x, we are going from one matrix to another. So we have to go here. I was going from x, y, z to u, v, w. So these matrices, how do you express x in the new coordinate system? So our new coordinate system is RGB. So how do you express x in the RGB? How do you express y in the RGB? Okay, so let's start with v. V is very simple. Because v is simply this one. So it is a unit vector. It goes in the 1, 1, 1 direction. So it is this one. This is the only unit vector that goes in the 1, 1, 1 direction. Okay, so that is very easy. And x is perpendicular to v and has equal g and b components. Okay, so we have a couple of constraints. So it has equal g and b components. So it is a vector of this form. It's a vector. So I will use a different color so that it doesn't get too flashed. So we know that x in the RGB is a vector that has equal g and b components. So it will be red, then g. So that is one, that is the shape of our vector. We know that it's perpendicular to v. So we know that x RGB times b RGB is equal to 0. And we know that it has a unique norm. So a norm of this is 1. How many vectors fulfill this condition? So we have 2 degrees of freedom, right? We have 2 degrees of freedom. We have one constraint. So how many vectors fulfill this condition alone? 1, 0, infinite, 2, only 1. Okay, that is one possibility. Everyone agrees. I have 2 degrees of freedom. I can change R and G. And I have one constraint. So how many degrees of freedom I am left? I'm only left with 1. Okay, so let's put numbers in this. Otherwise it gets too abstract. Okay, so you have 2 degrees of freedom. So let's say that let's put an easy number so that we can easily see what's happening. So let's say that b is 1, 1, 1. Okay, and I have this. So this constraint means that this is 1, 1, 1. So it is r plus t is equal to 0. So r is equal to minus t. So all vectors of the form minus 2g, g, they all fulfill this condition. How many vectors do we have? Infinite. I can change g as much as I like, and all of them are perpendicular to this. And they all have the shape. The green and blue components, they have the same value. So I have infinite. So if you have 2 degrees of freedom, you put one constraint, you are left 1 degree of freedom, that is D. So you have infinite possibilities. Okay, of these infinite possibilities, how many fulfill this second condition? Only one. So only one of these vectors will have this constraint, will fulfill this constraint. So if you have 2 degrees of freedom, you need 2 constraints to find uniquely, or to define uniquely your vectors. And which ones are those? This one. So it has more or less the same shape as I did. Okay, so in my case, it was minus 2g. So if you put -1, you have it. Okay, and this numbering form is just to make it a unit vector. Okay, what about y? Y has to be the cross product between these two. Now it's this one. So now I can put all that together into the matrix and construct this tree here. Because I know how to go from the HSV to the RGB. I know how to express all these 3 vectors. I have to do is put together into a single matrix. This is the matrix. So now, given HSV, you can automatically convert that into RGB. You have to remind that the coordinates in the HSV were having this kind of combined signs. Okay. So, but taking that into account, it is simply to multiply the vector that was here this vector that we have times this matrix. Matrix A. So you multiply and get the expression of that point in the RGB coordinate system. So, so here are some examples. So let's say that we take a plane, so R plus T plus B equals 3, 3, 4. Now, we can simply represent the red channel, the green channel, and the blue channel. So the red channel, so where is the red axis? The red axis is pointing there. The green axis is pointing here, and the blue axis is pointing there. So that is why you get more light in this direction, blue light in this direction, green light in this direction. So those are the RGB directions. And this is the Q value and saturation for the same plane. So we said the value, all these points, all these 4 points, they all have the same value because they all belong to the same plane. What about the saturation? The saturation was the distance from the gray point, the 1, 1, 1 point. So the gray point is here in the middle. So the saturation is the distance from the middle. And the hue was an angle. So you start, and it was the angle between your color and the red direction. So the red direction is here. So you have very low angles, and then as you go away, you have higher and higher angles. Okay, so now we can put colors on the hue. And now we can, for instance, we can take this image, we can go to HSV, you can increase the saturation by 50%. So you take, I know it is this. So we have an RGB color. We have, we convert it to HSV, and now I'm increasing the saturation by 50%. So I'm transforming this ethanol 1.5 ethanol. So this will be my new color, and then I come back to RGB. I don't know. Prime. I will have a new color, so I have to transform this color here into this one. And my transformation has been in the HSV space. So this is a point operation, the same one as we did with the gamma transformation, contrast transformation. But now we are doing our transformation in the HSV space that you can do it. Okay, so you do that, and now we increase the saturation. We have this image, we increase the saturation, then more points should become saturated. The histograms, more points are saturated, and the colors are more saturated here. We have more vivid colors. And you can decrease the saturation, and actually, if we decrease a lot the saturation, what should we have? A gray image. So you remove all colors. And also, you can do funny things. So, for instance, let's say that I have a color here. So, the white color. So, let's say that this is our triangle. And, this is our gray point. We have a color that is there, that has an angle. Okay, so you can have, say that this is X. This is the spectral X. The saturation was this angle up to that point. And I can take this point, this is an angle, so I can subtract 60 degrees, for instance. Subtract 60 degrees. It will be a new color, and that is my new color. Okay. So you take any point, any color in the triangle, you subtract 60 degrees, and then that is your new color. So that is called hue shift, because we are shifting the angle. Okay, so if you do a hue shift by 60 degrees, so instead of subtracting 60 degrees, you add 60 degrees, what happens is that the red becomes yellow. Why? What about this? So if I take this color and you add 60 degrees, now you're yellow. And if you take yellow and you add 60 degrees, you're green. So that is what's happening here. So red becomes yellow, yellow becomes green, and all the others also rotate. And now, this is your shifted image. So you look at an image and you make it more kind of yellow. Everything turns 60 degrees. That's it. Then you can turn 120 degrees, you can turn 180 degrees. We already know this transformation, we call it the complement. And we understand now better this name of complement. So if I turn 180 degrees, this red goes to cyan. And this green goes to magenta. And we remind from the previous lecture that this is exciting our cells in exactly the opposite way. So when we see red, we have high response in our red cells and low in green and blue. But when you have cyan, you have the opposite. So you have low excitation of the red cells and high excitation of the green and blue receptors. So you can play a lot with all your colors, for example. And you can compute all kind of histograms. So yeah, this. Here. No. Okay, so we have seen some color correction, but based on the HSP, space. We also saw it at the beginning, before getting into the HSP. We saw color corrections and color changes in the RGB, so you remember these ones here. Here, we were doing gamma transformations in the RGB. So you have a color, RGB, you apply transformation, you get a different color. You have a color, you transform it to the HSV, you transform, you have a different color. But these transformations don't have any, let's say, so I change them, but they're kind of uncontrolled. Do it now in a more controlled way. Sorry for this. Okay, so let's say that you have the original image, then you can change, apply this kind of transformations, and you can make whatever you want with it. But this is not very useful. Opposite. Yes. So let's say that this was the original image, but this doesn't exist anymore. What exists is this one. So you took a picture. The picture is now 20 years old, and now it looks like this because the paper degrades. How can you go back to the original? And the way to go back is to define color pairs. So you have to say, okay, look at this color here in the plane. Looks like this. This is the color that you have now. And this is the color that should be. So the red and green almost stays the same, but the blue, now it is much lower. It should be much higher. And you take another color, you say, okay, so the red and green stay, but the blue should be higher, not as high as the one before. And you take another color and you say the same. So for every color in the current image, you say how that color should look like in the original. Now you have pairs of colors. Okay, so now you have these transformations. So you know this color, that is the one that I want. This is the color that I want. Should be this one. This color should be this one. This color should be this one. Okay, but these are vectors. So try to find. Let's say that I have a pair of colors. So let's say that I have in the new image. So I will use. Okay, so that's fine. I have color 1. I have the new color that I have, and I have color 2. That is the old micrograph, how it looked like. So this color in the old image should look like this. And then I need to find a transformation between them, which is the simplest transformation that you can think of among vectors. So a sum. Okay, that's fine. Yeah, that is even simpler than the one I got. The next simplest one. Yeah, matrix multiplication. So I can try to find a matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. Such that when I multiply this vector by this matrix, get this one. Okay, and how many degrees of freedom do you have in here? How many numbers you can tune? I can tune 9 numbers. I have 9 numbers that I can change. So I have 9 degrees of freedom. How many constraints do I have by this color pair? 3. So this red should turn this way. This green should turn this green. This blue, this blue. So I have 3 constraints. So I have 3 equations, 9 unknowns. So not enough. What if I add a second constraint? So I have a second pair of colors. Now I have 6 constraints. What if I add a third constraint? So a third pair of colors. Now I have 9 constraints. So I have 9 constraints, 9 unknowns, and I can solve it. What if I add more? So in general, I can write these constraints. So I can say R mu 1, all the others, R mu 2, all the others, R mu 3, all the others. I add a new color, a new color pair, and you can add as many as you like, times this matrix A should be equal to RO1, the others, RO2, RO3, RO4, and the others. You agree with that? So, how many constraints? Let's say that you have only 4. So, how many constraints do you have? You have as many as colors, as components of colors. So, if I have 4 pairs, I have 3 components in each one of the pairs. I have 12 constraints. But I have only 9 degrees of freedom. What do we do? So let's try to formalize this. Okay, so I have a matrix. This is a matrix. I will call it a Y. And this is A. This is another matrix that I will call it X. So I try these 2 things to be the same. So when you take this matrix multiplied by A, multiplied by A, you try to get Y. Okay, but then we have 9 degrees of freedom here, and I have 12 constraints. So what do I do? Least squares, right? So least squares means try to find the A such that the distance between these 2 things is as small as possible. This is called least squares. It's least because we are minimizing the squares because we have a square. Okay, and there is this is not a difficult mathematical problem, but there is a very simple way of finding this solution. Okay, so what would I like? I have to solve this equation system. So I would like to say A is equal to Y x minus 1. Can you do that? Yes? Everyone agrees? Everyone agrees? We can do that. Yeah. Okay, let's think of the size of X. So what is it? How many columns do we have? We have 4 columns. How many rows we have? We have 3. So this is a 4 times 3 matrix. Can we invert the 4 times 3 matrix? You cannot. You can only invert the square matrices. So this is not well defined. So this thing here is not well defined. Okay, so, but let's play a trick. Okay, so we start with y equal ax. Let's look at the sizing. So we said this is 4 times 3, this is 3 times 3, and this is actually I did it wrong. I should have put the a. I should have put the a on the other side. That put the a here. This kind of things you notice when you put sizes. Okay, so then we have to reverse this back. Okay, so this is x minus 2a. Okay, and this is 4 times 3, and this is 3 times 3. And again, you cannot take this x to the other side. Okay, but there is something I can do. Okay, so I can multiply by x transpose. So I can do x transpose y, x transpose x, okay, right. Multiply with x transpose from the left. Okay, so let's see what are these sizes. This is 3 times 4, this is 4 times 3, this is 3 times 4, this is 4 times 3, this is 3 times 3. So size like it is consistent. And now this is a 3 times 3 matrix. So you can invert it and put it to the left. So you can say x, x transpose x minus 1. This comes from here. This comes from here. So I'm taking this to the other side. Then continue x transpose y transpose a. And this is my calculation. So the matrix that takes the old colors, multiply by that matrix, and you produce the new colors, is this one here. X transpose x minus 1 x transpose y. So this is what you want to get. This is what you start from. Okay, so that is what is explained in all these slides. Okay, so all these slides here, you see the same kind of expressions. It depends whether this goes in front or behind. It depends on how you arrange your vectors. Okay? How I arrange my vectors. So these are row vectors, and I have written column vectors. So that is why the change of the order. All these squares is the same. Okay, so now we apply that. Have pairs. So now once you have all this, so you construct your x and y matrices, and you compute the A. And if you use only 3 pairs, the matrix is unique, so you don't have to play all these least squares 3. But so you can invert one of the matrices. And you see that okay, this is what we wanted, this is what we have achieved. So it is better than before, but not much better. More colors you add, so the more pairs that you add, the better the pairing will be. So now you add more pairs, and then you have something that is much more similar to what you want. Yeah.
But you have inverted the x there, and you said that we can multiply it.
Yeah. This one, yeah, this equation here is only correct when you have 3 mappings. So if I have 3 mappings, this matrix, this one here is 3 times 3, and that can be inverted. Now, when you use the 4 times, so this is the original, this is the corrected. So you get a much better here. A little bit of MATLAB code. Any question? So we have seen 3 ways of changing colors. So the first one is acting directly in the RGB. The second one is acting on the HSV. And we have already introduced HSV as a new way to represent colors. And the third one takes 2 sets of colors, and you want to transform one into the other. And then we have found the matrix that makes this translation, this conversion. Questions? No questions. Okay, so let us see one of our icon things. So let's see an example in icons. So if you look for there is a section in icon called colors. So you can go up. You see here colors, and I have chosen one of the articles. That is this one. And here in this article, what they will do is they will take one of these input images and they will transform it into the HSV space. So they will transform it into HSV. And then in the HSV, so here you see hue, saturation, and intensity of V. And then in this space, they will make beams. So you can compute the histogram. You can divide that histogram into different regions. How many regions? So you can put, I have chosen 6, 5, and 5. And then all the colors within a beam will be assigned to the center. So this is another possible transformation that you can do. So let's talk only of the V, for instance. So this is V. This is V. This is the histogram of V. And then the V has light. And then I divide this into 4 regions. And these 4 regions, all these values here will be assigned to this value. All these values here will be assigned to this. So now I have only 4 discrete values in my list. And I do the same for the other hue and saturation. And now you see, and now you come back. So this is another way to transform images. And this is the way back. Okay, so this is our transformation. And but it's a very rough, so we are using very few colors. You see, we are discretizing a lot of our colors, but not in a very bad way. I would say the colors mainly are preserved. So we see the boundaries and so on, that is unpleasant. But the colors themselves, there is a lot of small degradation here, so you can think of the color cube. We are moving around an area, and we are substituting all that area by a single point. But it is not terrible transformation. And something nice is that now you can annotate which are the colors that you needed. So what are the different colors that you have used? And these are the different colors. So these are the different colors that you have used. Now you have this